عالية. بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Welcome you. Good afternoon everyone. Welcome you to the final defense presentation of Mr. Lotfi Surashman. And Mr. Lotfi earned his bachelor degree in physics from the Institute of Technology Bangalore in Indonesia in 2011, focusing on nuclear power plants. He then completed his master's degree in physics from KPUBM in 2018, specializing in laser spectroscopy for environmental and geological applications. He is currently still a student member of the SEG and ENGE. His research interests include machine learning, seismic inversion, and reservoir characterization. His PhD research focus on post-stack seismic inversion using machine learning with the title Machine Learning-Based Acoustic Impedance Inversion with Optimized Reservoir Characterization for Drilling Location Recommendations and Reserve Estimation. And Lutfi will have 30 to 45 minutes to present. After that, I will open the floor for questions from the public. And after that, we'll take a short break, and only the committee will reconvene with you for a closed session. So good luck, and the floor is yours.
Thank you so much to my Professor Abdul Latif Al-Suhail, for giving me time to start my presentation. The title was already explained, so I will continue to the outline. The outline of my presentation is introduction, background, motivation, gaps, and objective. And then we have the research projects. Mainly we have 3 projects: single ML based model acoustic impedance. Project 2 is drilling location recommendation, and project 3 reserve estimation. Then we draw the general conclusion. For introduction, our title is post-stack seismic inversion using machine learning. Post-stack seismic inversion is to compute acoustic impedance, which is density of the bulk time acoustic velocity. Let's call it Z. Using machine learning, we use input features of seismic attribute, depth, and retrieval time, and our target is acoustic load, which is one type of well load, to predict the acoustic impedance. As the comparisons, we use recursive inversion to compare our result, and in low frequency, we have band limited impedance inversion. Our motivation of the study is why is it important to understand the low acoustic impedance profile. It gives us accurate information, better estimated porosity, permeability. Further, we can define the net pay for drilling decisions and research. As we see here, the picture from Becky et al. 1979, it was published in Geophysics, give us an insight that at low acoustic impedance here, this corresponds to a gas bearing sense. So low acoustic impedance profile will give us insight on the oil and gas exploration mainly. So why low acoustic impedance? As I said before, we want to study the relations with the porosity. So we can define we can further derive with the definitions from the acoustic impedance, which is density times acoustic velocity. From the profile of density with porosity, we can see that decreasing density imply higher porosity. This can be understood by the physical intuition. As we have lower density, we have more void space, implying higher porosity. Also, once we have more void space, this will give us lower energy of compressive propagation, because this P-wave velocity is a compressive wave. We can think of like a spring which has a constant, and this constant is related to the elastic constant. The lower the elastic constant, which is higher void space, we have lower energy of propagations, which means lower velocity. This is what I understand. So the low acoustic impedance, which is low density and low velocity, can be better explained by having higher porosity from this previous two relations. The next relations, we are trying to understand what is the relation between acoustic impedance and water saturation. But before I miss something, the importance of this acoustic impedance to low acoustic impedance to higher porosity will be important for us for the net pay conditions as the main drilling recommendations. And the relations of acoustic impedance with the water saturations can be better explained by density and P-wave velocity as previously we have done. Here we see that the relations between density and water saturation. We can imagine the material, earth material like rocks, matrix, and the fluid. With lower saturation, it will give us low density. We can just imagine about this, and then lower water saturation can be explained by lower P-wave velocity, lower energy of compressive propagations. So the resulting acoustic impedance, which is multiplication between density and acoustic velocity, will give us the same profile. Low acoustic impedance will be correlated with the low water saturation. And in summary, you can imagine as a 3D profile between low impedance profile, it corresponds to the high porosity and lower water saturation. This will be very important for us to compute the hydrocarbon pore volume, because the hydrocarbon pore volume will be proportional to the porosity, and 1 minus porosity. The less water content we have, the higher oil we have, the content of hydrocarbon we have. This is the assumption. So you can see here the lower impedance profile in this region. Mostly we will be having we will be having a better estimation of the research with this low impedance profile that has high porosity and lower water saturation. Our research gaps our band limited impedance inversion has low frequency, and so it gives us it is underestimating the acoustic impedance and gives us a biased reservoir property. The next gap is single model lack of accuracy, and so far there is no integrated workflow that can be computing from acoustic impedance until the drilling location and reserve estimation. Our objectives are the first objective to compare between several single ML model to predict the acoustic impedance. The second objective is to use floating state regressions, or we call it V-star, for the best prediction of acoustic impedance for drilling location. And the last, we are trying to find the global optimization for reservoir properties to compute the estimated results. Let's call Z hat as the predicted acoustic impedance. So the first project is acoustic impedance prediction based on extended input of seismic attribute using multilayer perceptron, random forest, and extra tree regression algorithms. It was published in a Q2 journal, Petroleum Exploration and Production Technology, with an impact factor of 3.2. Our literature review, we found some existing machine learning model that is artificial neural network, random forest, support vector machine to compute different parameters. And in our works, we use the baseline study of Mardani and Tras in 2020 to use seismic and log data to compute the acoustic impedance. And this becomes our baseline. The methodology developed by Mardani is using the input of seismic attribute in seismic trace resolution, and then I edit with depth and two-way triple time. With improved model in addition to MLPR, we use RFR and EPR with the target of acoustic impedance to predict the acoustic impedance. And to compare this, our ML method, we use input of seismic and log data to compute the recursive inversion with a specific type of low frequency domain. We have band limited impedance. Our ML model, the first one is multilayer perceptron regression. We have seen here multilayer perceptron is multiplying the final weight with the activation function here. And this activation function is actually the middle weights times the input features. So once we are able to find the MLPR predictions, we do the incrementals of the final weights and then the incrementals of middle weights. Then we make the updates of the weights of the final and initial weights, do the iterative procedure until we find that the MLPR predictions close to the true value. The second is random forest. Random forest is begging with decision trees on random subset of features. So random forest predictions is taking average of the decision trees for every bootstrap samples on the set of training data. So this is the predictions of random forest. What is the difference between random forest and extra tree regressions? It's on the features, input features. APR domain is the full set, the whole set of features, while random forest is only subset of the input features. For data sets that we have, around 5,000 samples, the input features is depth, weight, triple time, and 9 attributes. We do the training on the input features on 18% of data set, with training and testing can be seen in this proportion. For the prediction part, it's on 20% of data. After we train the model, we apply it into the input features, we get the predicted acoustic impedance. So these are our input features. We see mainly we have amplitude until integral, second derivative, quadrature amplitude, gradient, until gradient magnitude. This can be classified as the amplitude derivatives of the amplitude. Derivation derived all properties derived from the amplitude xt. Others also have the same derivation from the input features, but the second classification is about instantaneous frequency. The last classifications is phase and cosine of phase. So the MLPR predictions close to the value of Mardani, it was 0.85. Mardani's value was 0.88. And then we improved with the random forest and extra T regressions. This was the reason why my paper was published actually. And this is based on this result. So we see that the single ML model predictions is better than BLIM. For the second projects, we are trying we studied why our single model has limitations, and is the voting in the single competitions of our single model better than the voting of cooperative teamwork, which is our VSTAR, field voting stack regression. This study was published in scientific report, a Q1 journal with impact factor of 3.9. The methodology is the same. Here we only use VSTAR as our new model. So acoustic impedance using stacking regression. Stacking regression is linear combinations of all single model that we have multiplied by their own weight here. So to find the solution of stacking regressions is actually to find this weight initially. To find this weight, we can use least square of the true and predictions under non-negativity constraints. In more detail, acoustic impedance prediction using stacking regression can be started with the level 0 datasets. This level 0 datasets is like we had seen previously, consisting of the input feature X and acoustic impedance target Z. So we have 3 single model regressions, and all of them under 3-fold cross validations and grid search can give the best model predictions, giving us the level 1 dataset, which is Fx, Z. Once we aggregate the predictions, we get the initial weight, becoming the initial linear combinations. To get the improved predictions, we need to regularize using this meta-learner or regularizer, becoming our stacking regression predictions. These are the final estimator regularizations that we use. We have 4 final estimator, can be divided into 2 different types, which are penalized linear regressions and linear SPM regression, linear support vector machines. The penalized linear regressions are ridge, lasso, and elastic net. In the coming slides, I will show how the movement of the penalized linear regressions from the perfect predictions as we increase the value of alpha, and we will see how the movement of linear SPM regression with respect to the perfect predictions as we increase the value of C here. So acoustic impedance predictions using voting regression. The next step, voting single regressions is taking average from the single best model that we have, while voting stack regression is taking average from all stacking regressions with 4 different final estimator that we have seen previously. The results and discussion here, hyperparameter outcomes mostly are for the final learner, meta learners, because for the best model we just hide it to make it visible with the grid search. And these are the published alpha and C value with L1 ratio. L1 ratio is the ratio of L1 norm. What we are able to see in this slide, it's about ridge, lasso, and elastic net string edge, which means the movement towards 0 as we increase the value of alpha. For the ridge regression, ridge, for the geologists, they can better understand what is ridge. Ridge, mountainic ridge, oceanic ridge, this is the same term. Often we find solution of this ridge regression as we move toward the increasing value of alpha. Ridge is, what is ridge? This is just like extension in the mountain, and narrow, long and narrow extensions on the mountain, right? So we can see as we increase the value of alpha, often we find the optimum weight something like this, as we have seen the ridge. What is lasso? Lasso regression is least absolute shrink edge and selection operator. Least absolute shrink edge means we use L1 norm as the term for penalizing this term. For L1, for L2, which is the ridge, we use L2 norm square to penalize this sum of square error between two and predictions. And this equations is actually for the equation of elastic net combining between the L1 norm of lasso and L2 norm of ridge. So elastic net regression is a grouping effect from ridge and lasso, with L1 ratio is how many percentage of L1 norm of lasso effect in this elastic net. Here we use the L1 ratio of 10% for the from the lasso, giving us dominant effect from the ridge. So this elastic net is dominantly affected by this ridge. That's why the profile is similar to the ridge regression. Now we are trying to see how, as we increase the value of alpha into the ridge regression. Can we see the movement? The movie here? Yeah. Maybe I need to reset.
I think you have to touch maybe the left first, in the middle, and the
Yeah, it's moving. Yeah? See, as we move this alpha, as we increase the value of alpha, this W will decrease because we need to minimize this addition of the objective function so that the ridge predictions move further from the perfect predictions. Similarly for the lasso, it's moving slowly because we use L1 norm, and the R squared decrease slowly compared to the ridge. While the use of this elastic net, it moves faster and further from the perfect predictions as we increase the value of alpha because of the grouping effect between the ridge and lasso. What is the purpose of doing this? To find alpha, optimum alpha, which gives us the best R squared, the best predictions of acoustic impedance. Now we are trying to see what happened as we increase the value of C with the R squared. What do you think? So the linear SPM predictions create the factor which moves the linear SPM predictions toward positions where majority of the points are available inside the acceptable margin of error epsilon instead of creating a linear line. So because of these equations, we need to minimize the difference between the additions. Once we increase the C, we will minimize this. This term means we make the two interactions closer. So that's why. So our solve weight here in our published results give us the optimum weights after regularizations that we saw previously with different objective functions to find alpha and C. So once we get the value of weight, here dominantly the weight is the dominant weight is ATR, which means ATR is the best of all of the three methods we have. And then finally we get the predictions of stacking regressions by substitution into the equation using the optimized way. So this is our results for floating stack regression by the mean square error, floating singular regressions, and the stacking regressions. What I want to discuss here is what is the difference between overfitting, underfitting, and good or best fittings. Overfitting is low bias, high variance. For underfitting is low bias. This one for what I said, overfitting. Overfitting is low bias, high variance. Low bias, high variance. Underfitting is high bias. This bias is red. High bias, low variance. What is the best fitting? It should have low bias and low variance because it has optimum model complexity and the lowest error here because of the regularization and penalized regressions that we have seen before. So our floating stack regression has the least error because of low bias and low variance, and it was proven by the highest R square here. The highest R square, even though it has the most expensive computing time. That is the pros and cons. Compared to the floating singular regressions, it is the slowest but the least prediction. So this result is our acoustic impedance predicted with different methodologies, with band limited and with all ML model compared with the true value. Here we have seen our R square and computing time. The P star is the most expensive, about 400 seconds. The stacking regressions at the average is around 100 seconds, and the floating single regression is around 20 seconds. We can also see from the learning curve of floating stack regression here has the least bias, while the floating single regression has the highest bias. So this result confirms that the P star is better than PSR and better than the band limited impedance inversion. This is the heart of my study, which is the optimized reservoir characterization. After we obtain the predicted acoustic impedance with different methodologies, we transform into porosity using this exponential regression transformation, physics exponential regression transformation, and then using permeability, porosity to permeability using this power law transform. This equation is actually a pattern. You can find this porosity to permeability as a pattern in carbonate permeability. So once we are able to define these equations, we will find what is the value of these empirical parameters with optimization algorithm with the cost functions that we need to define. Here the cost functions means every good reservoir should have a cutoff or threshold where the distance between the cutoff or the threshold to the extreme values, which are the minimum and maximum, should be optimized. In this case, should be minimum. And this is the reservoir threshold that we have from the literature. Once we get this reference threshold of porosity and permeability, we can define the initial value and bounds to solve the value of A, B, C, D. This bound should include this threshold. That's why we use LBFGSB algorithm. Once we obtain the solution of the empirical parameters, we substitute into the equation of porosity and permeability. Then we get this profile of reservoir porosity and permeability. Now we are able to see that using this threshold, where the reservoir, the condition of the threshold porosity and permeability that are greater than the threshold, that are the drilling locations that we can be recommended here. anywhere, any locations that has the threshold greater, any locations that has porosity and permeability greater than their threshold can be shaded in this zone. So we can see that in this shaded zone, the plotting of stack regressions line is higher than plotting single regressions, and it's higher than the blend method. So the with the R square of V star highest. The key findings of project 2. So we can see that the ranking of elastic net is higher than ridge, similar to lasso, and higher than linear SPM. But the ranking of plotting stack regressions is always consistent. V star is greater than VSR, greater than blend. So this V star is the best predictions of drilling locations based on ML method. Even the time is most expensive. The third project, sorry, I missed to say something. This is why in the first introductions, why do we have low impedance profile here? We introduced in our introductions why it is important to have low impedance profile, because now I prove the introduction that at this low impedance profile we have high porosity, high permeability, and this is with different methodology becoming our contributions into the science with different methods compared to the existing concepts in the introduction.
But you have 10 minutes.
Yes, Professor. Yes, for this global optimization and research estimation, we have published in the results in engineering, a Q1 journal, with impact factor of 7.9. The methodology are the same. We just use the existing optimized porosity, extend the optimized porosity to be net pay and hydrocarbon for volume until reserve estimation, and then the outcomes of hyperparameters, the above table for random forest and extra tree, below table of MLPR. The most interesting result in this study is the global minimum that we get by running the LBF-GSB around plus minus percentage of the perturbation into the initial value with this setting of parameters. We find that at around plus minus 3% perturbation to the initial value, we get the global minimum of error. The resulting empirical parameter then substituted into the porosity and permeability equations, and then we get this porosity and permeability. At low impedance profile, we have high porosity and high permeability. Which method is the closest to the true value can be obtained by the sum of square error between the predictions and the true value. From these relations, we see that the extra tree regression has the least sum of square error, which means that the EPR has the least value, the closest to the true value. Sorry. So for the next session, the next slide is about hydrocarbon for volume and reserve estimation. This parameter, water saturation average, formation volume factor, and interval thickness is useful to compute the hydrocarbon for volume and the reserve estimation. For the classification of net pay based on our net pay conditions, give us the thickness of net pay. We see that the net pay of thickness from the true value is the ATR is closest to the true value. Once we use the net pay conditions, we can get the binary masking. We call it hard mask. Give us 0 and 1 for computing the hydrocarbon for volume. 1 means the conditions where porosity and permeability are higher than their threshold. 0 means the other conditions not fitting with this net pay conditions. So where shaded zones contribute to the HCPP but unshaded zones are excluded. In the right side, we have softmax for computing the pore thickness classifications for pay zone and IP and unpay zone for the transitions in between using the mesh value of 0 between 0 and 1. So now we are trying to compute the accumulative hydrocarbon for volume by summing all incremental HCPP in every depth sample. In the first depth sample, for sure we will have zero incremental because this delta will be zero. And then in this shaded zone, we make this mass by multiplication with 1 because this shaded zone is the phase zone. That's why we get increasing linear line. And for the unshaded zone, we multiply by 0 in this mass so that we have this linear horizontal lines. We move until the final depth sample. This is the total accumulations, giving us the total HCPP of the true value higher than the APR. APR is greater than random forest is greater than MLPR, and all of them are higher than limited impedance inversion. Then the original oil in place is proportional to the accumulation of hydrocarbon for volume. That's why the profile of ranking has the same as the accumulation of hydrocarbon for volume. Also, the total result has the same trend. Only we multiply with the recovery factor of 30%, which means 30% of oil can be economically recovered. The key findings of Project 3, as we have seen, the 3 single model are relatively accurate under hyperparameter and global optimization, and the consistency tracking the same as the Project 1 that we have. And the last is the field scale research evaluations are obtained. So these are the conclusion. We can see that Project 1 and Project 3 has the same consistent ranking. The difference is only the use of hyperparameter and global optimization for reserve estimation in Project 3, and it is feasible for reserve evaluation. For Project 2, the consistent ranking is V star higher than VSR and greater than BLIM, so it becomes the best predictions of ML method, even it has the most expensive computing. For acknowledgement, I would like to thank to Allah Subhanahu wa Ta'ala for blessing me with the scholarship from CPG to UPM until I'm able to publish 3 papers and have opportunity to defend my dissertation. Also, I would like to thank to CPG for giving the scholarship until I'm able to bring my father and my mother for Hajj. My father passed away in 2014 for ICANN. Alhamdulillah, I performed on behalf of him. Very thankful to CPG for this. Thanks to my advisor, Professor Abdul Latif Al-Suhail. Thanks to Professor Abdul Aziz Abdul Rahim. Thanks to Dr. Salim Kaka. Thanks to Dr. Sharif Mahmud. Thanks to Dr. Wezo. All of them are my dissertation committee. I would like to thank for their availability to give advice and evaluate my dissertation. I would like to thank all people, all audience coming to my presentations today in this room, all CPG, KFUPM, faculty and researchers, international students, also Indonesian students and community. Thanks for coming to my presentation. I would also like to thank the audience online, my family, my mother, brother, sister, friends, relatives. Thanks for listening. I would like to return the time to Professor.
Thank you, Dr. for this very nice presentation. I open the floor for any questions for the public audience. Dr. Wong, you have a question?
Yes, please.
Yeah, not a question per se. I just want to commend him for this excellent research. The work has gone through peer review, and there's no need to ask questions.
Thank you, Dr. Paul, for your comments. I really appreciate. Hope to collaborate with you soon in another research.
So if there are no questions, I will pick people to ask. And you have the chance to ask or say a comment. Otherwise, please ask.
Yes.
Yes.
Thanks.
Thank you very much. Thank you very much. Okay,
You can just wait. It takes a second or so. A few seconds.
Thank you very much, Mr. Lutfi, for this wonderful presentation. Actually, we did masters together here with Lutfi, though in physics, but he jumped to CPG. So it's a wonderful work. Is there any room like to improve the machine learning work, maybe by considering some hybrid models or something in the future?
The improvement for thank you so much, Mr. Yakubu, my colleagues from physics department, for asking the question. To improve the machine learning models, as we have seen here, previously we only use 3 single model regressions, which is MLPR, RFR, and APR, especially for my second project. My second project, this one. We only use 3 machine learning model, which is extra-tree regressions, random forest, and MLPR. What happens if you use different machine learning model for the single base model? Are we still able to find the stacking regression similarly with the best predictions, or different? Also, we only use this 4 meta learners. In the literature, we have many meta learners. I just use 4 of them. So this can be the next stage if we want to study only the machine learning. If I try to answer in more detail, we are only using machine learning as, very hard mathematics. We don't imply physics informed V-star, for example here. Physics informed V-star can be applied in this next. It will be very interesting because we will honor physics very well, geophysics very well, geology very well. Thank you for this insight and comments.
Nobody is asking, that's why I have to ask.
Yes, please.
Yes, Ali.
Mr.
Thank you for your
Yes.
presentation. I wanted to ask, why is it that you focused solely on acoustic impedance for reservoir characterization, as opposed to pre-stack attributes like non-neuro BBBS, which are better fluid discriminators for reservoir characterization?
Okay. Thank you so much for the question. So the honest answer is the methodology I try to develop and the data set that I get from the literature fits well with the post-stack seismic inversion. In the future, it can be interesting by incorporating the pre-stack inversions. I previously worked with Professor Abdulatif about this. Hopefully, it can be incorporated. Also, here why post-stack? Because why acoustic impedance? Because I want to compare it with this seismic inversion method, and we want to overcome the band-limited impedance inversion. The band-limited has many hidden aspect, geological aspect here, like the lower frequency domain. It is hiding the thin beds, in geology. In thin beds, we have high frequency because of oscillating between seismic waves in distinct beds because of the high velocity, because the close or the very thick, very thin situations in the geology, it will give us a very high velocity of oscillation, and it should give us the high frequency, but it was not able to be shown by this very limited impedance inversion, as we have seen in this location around 3,300 to 3,400, for example. These very limited lines, it's just horizontal, so it lost many information. That's why acoustic impedance. I want to study this. Thank you.
Do you have a question?
Maybe there is question to the.
There is no other question. Thank you very much.
Yes,
We will. Are you inviting the students and audience to some refreshment?
Yes, but I want to make sure if all the Indonesian foods are already. So yes, it's already prepared. Yeah, thank you. Because I prepare satay, bakso, molen. It's Indonesian food. If it is already ready, please separate the package for my dissertation committee. Other than that, I want all of you to finish.
So what I suggest is that we take now students and everyone can grab something, or maybe we'll pray and come back for the closed session.
Yes.
So the committee. Thank you very much.